Okay, so hi everyone. So today in this video, we will be discussing solutions to the problems of Code Forces Round 881 Division 3. So we will be discussing problems from A to F1. So let us move to the problems one by one. So this was the first problem, Sasa and array coloring. So you are given an array A consisting of n integers and you are asked to paint the elements, right? And you can paint each of the elements in any of the colors, and after painting each element with any color you have to find the value of this, which is what is the maximum value of the element colored in that color minus the minimum value of the element colored in that color, and then you have to sum it up, and that sum should be the maximum basically. So you have to calculate the maximum possible cost of coloring. Okay, so let us see how we can do this. I can share my iPad screen. So, so basically you are given some array, right? Let's say the elements are like 1, 3, 5, and 8, right? And you have to color these with some colors. So obviously the order of the elements of the array does not matter. So what we can do, we can first of all sort this elements in the array. So it will look something like this: 1, 3, 5, 8 in the sorted order. After that, we have to color it with some colors. Let's say we color it with color 1, 2, or you can say it, let's say we color these two elements with the same color and we color these two with the same colors. So what will be the cost in that case? That will be nothing but this will becomes 3 minus 1 plus the color uh, blue is used to paint 5 and 8, so the maximum is 8 and the minimum is 5. So from here you get a cost of 2 plus 3 is equal to 5. Okay, so basically in this way you can color each of the elements with any color and you have to maximize the total cost. Okay, so let us say what happens if we color all the elements of our array with a single color. So let's say if the value of the elements are like a0, a1, a2, so on and so up to a of n minus 1, right? Let's say these are also in increasing order because we have sorted this array. What happens if we color each of these elements with the same color? So what does the cost come out to be in that case? That's is nothing but a of n minus 1 minus a of 0. That is the difference between this and this, right? But you see, you can also get this cost by coloring the first and the last element with the same color and coloring the remaining with some other color, right? So even if you color only the first element and the last element with green color and color the remaining elements with any other color, you will still be getting a cost of this much plus something extra as well you can get. So why? Because if you color this with green, you will get a cost of this. So what you will do, you will color this one and this one with the same color plus now you are left with this subarray. So again by the similar logic you can say that you will color this one and this one with the same color so that you will get a cost of this much. Okay, so in a similar logic what you can say is that the first and the last elements should be colored in the same color, then the second element and the last element should be colored in the same color, and so on and so up to. So basically in this way your cost total maximum cost will come out to be a of n minus 1 minus a0 plus a of n minus 2 minus a1, like this. That is the difference between this plus the difference between this plus the difference between this, like this. So this is clear to everyone, right?
Yes.
Okay, so let us now quickly move to its code then. Okay, so just take your array A and then just sort it, and after that you just iterate for I is equal to 0 to n by 2 and add this, which is a of n minus I minus 1 minus ai. So see, when I is equal to 0, this is nothing but n minus 1 and this is a0. So definitely there will be n by 2 such pairs which you can form, right? So that's why I'm iterating for I is equal to 0 to n by 2, and I am finding the corresponding last pair minus this first pair and just adding it all. Okay, so let us now move to the next problem, which was long. So in this problem you are given an array of length n, a1, a2, so on and so up to an, and we can apply many operations on this. And in one operation, you choose some integers L and R, which are within the range 1 to n, and you just multiply all the elements of the array from L to R by -1, right? So what it means is that you can basically flip the sign of all the integers in some range, right? And you have to do it in such a way that the sum of the numbers in the array is basically maximized. Okay, so you have to find the maximum possible sum of the numbers in the array, which can be obtained by making any number of operations, as well as what is the minimum number of operations that is required to achieve this maximum possible sum, right? So let us see what we can do for this. Okay, so let's say your array contains elements like 3, -4, 2, 0, and -6. Okay, so what do you think? What can be the maximum possible sum? Definitely, the elements which are positive, they will always contribute a positive value, right? But what about the elements which are negative? What if we can somehow make them positive? So definitely that will give you the maximum possible sum. So what you can do, you can just flip the sign of these elements, right? You can simply choose this, like if index I is containing some negative value, you can choose some L and R simply as I, and that will just flip the sign of it. So in this way, you at least know that the maximum possible sum, sorry, the maximum possible sum will be nothing but the sum of the absolute values of each of these elements, right? So in this case, for example, the maximum possible sum will be 3 plus 4 plus 2 plus 0 plus 6, right? And definitely you cannot achieve anything greater than this sum because each of the values is positive in this. So now you know what is the maximum possible sum. But how can we achieve this maximum possible sum using minimum number of operations? So let us see what we can do for this. So see here, if you have these, or let's say another example, let's say if you have elements like this, 3, -4, -5, 6, 0, -2, 0, -3, like this. Okay, so what we can do, just a minute. Okay, so I was explaining problem B. So let me just again revise it for you. Basically, you are given an array A, and you have to find the maximum total cost, or like the maximum possible sum. And you can just choose some segment L to R and flip the sign of all integers within this range. So definitely the maximum possible cost will be simply the sum of the absolute value of all these values, because you can always flip the sign of a negative integer by simply taking I to I and just reverse that integer itself. So that is the minimum total cost. Now I was telling you how you can find minimum, sorry, that was the maximum total sum of the elements. Now I was telling you how we can find the minimum total operations needed to do this. So let us say we are starting traversing this array from left to right. So whenever you get a positive elements, like you don't have to do anything, no operation. So you can simply skip, right? Now, when you get a negative element, you know that you have to apply an operation. So what you will do, you, since you need to minimize the operation, you will keep on checking like, okay, how much negative continuous elements are there to my right. So for example, -4 is negative, -5 is negative, then 6 is not negative. So you will just stop there. So now you can see that from this to this, you will simply apply one operation, right? Then again you move ahead, 6 is positive, no need to do operation. 0 is positive, 0 is again not positive, but this is 0. So again, this does not have to be applied any operation on here. So you just simply continue. Then -2. So -2, definitely there needs to be applied an operation. So you just continue -2, then 0. So even if you get a 0, still you continue on searching, because it might be the possibility that ahead there is again a negative element. So that's why you keep on continuing. So if you keep on continuing, you can go till there. So in this way, you need to apply here two operations, one on this and the other on this. Okay, so all you need to do here is to just simply iterate, check if it's a negative, how much negative elements, like skip all the negative elements in one go. And if you are 0 or positive, skip it. And while you start with a negative element, even if you get a 0, you keep on going ahead, don't stop. Because if you stopped here, might be you will have to uh, do two operations, although you can do it in one operation only. Okay, so any doubts in this? Okay, so if there are no doubts, we can move to its solution or code. Okay, so here, as you can see, I have taken array A, and then I am just iterating through all elements of the array A. And if AI is greater than or equal to 0, I simply add it to my answer. Answer is basically the total sum, maximum total sum. So if it's a positive, simply add it and continue. And also if it is 0 also, then also you just add it and continue. Otherwise, you need to apply an operation because AI is negative. So you just try skipping as many negative elements as you can. So start a loop on j. So while j is lesser than n and aj is negative or even 0, you just keep on skipping that and keep on adding the absolute value of it, because for -3 you add 3, so the absolute values. And then you just move to the next, like j. So I is equal to minus minus j, so j minus 1, and after that this I got incremented, you move from the current I to the j where it was positive, or where it was positive. And at the end you just print what is the maximum answer and what is the minimum number of operations required. Okay, so just in case if you have any doubt, you can simply interrupt me and ask me. Okay, so let us now move to the next problem, which was sum in a binary tree. So in this problem, you are given a binary tree like this. So a binary tree is a tree for which each node has like at most two children. But in this case, it's given that for each node there, it has like exactly two children. Okay, so for example, it's given that tree has one vertex 1, then 1 yeah, adds two children to it, number 2 and 3. After that, so vertices are added in the increasing order, like 1, then 2 and 3, then 4 and 5, then 6 and 7, like this. Okay. Now what you have to do, you have to find the sum of vertex numbers on the path from the vertex with number 1 to the vertex with number n. Okay, what is the sum equal to? For example, if you consider 4, then what is the sum of all numbers from 1 to 4? That is nothing but 1 plus 2 plus 4, that is 7. Similarly, you will be given any n. The n can be in the range 1 to 10 to the power 16, and you have to print it. Okay, so let me show you the solution for it. So if you see the structure of graph, like 1, the children of 1 are 2 and 3, then the children of 2 are 4 and 5, the children of 3 are 6 and 7. Similarly, you can draw it like this. So if you observe here, the children of node I are nothing but 2i and 2i plus 1. Okay, for example, 3 children are 3 into 2 6, 6 plus 3 into 2 plus 1, that is 7. Okay, so the children of I are 2i and 2i plus 1. And you can also alternatively say that the parent of a vertex v is nothing but v by 2 taken floor. The parent of v is nothing but the floor of v by 2. For example, for 6 it is 3, for 7 it is 3. Why? Because 7 by 2 taken floor is nothing but 3, right? So in order to find the sum of all the paths, all the nodes from 1 to some vertex n, you just keep on moving ahead. For example, if you have to find till 9, you add 9, move to its parent, that is nothing but 9 by 2, that is 4. Add the value 4, move ahead. That is 4 by 2 is equal to 2. And again add 2 and add to its parent, that is 1. Add 1 and 1 by 2 it's getting 0. So stop as soon as you hit 0. Okay, so this is the simple approach that you can do. Okay, just keep on moving to its parent, and moving the parent of V is nothing but going to V by 2 taken floor. Okay, now what will be the time complexity of it? Since you are continuously, like, you start with V, divide V by 2, then V by 2 by 2. So in the worst case, it will take you O of log n. So if you're starting with n, so whatever is the value of log n, you will move at most those many steps up. Okay, so it will be well within our time limit as well. So if I try to show you my code, so all you did, or all you can do here is that simply take n, then while n is not 0 or n is positive, add the value of n to your answer and make n the parent of n. So the parent of n will be nothing but n by 2. Okay, and just print the answer. So anybody have any query on this? Okay. Okay, so if no, then we can move to the next problem. Okay, which was problem D. So in this problem, it's called apple tree. So here you are given a tree which is a rooted tree of n vertices with root in the vertex 1. And this tree is very unusual. It grows upward, so it's normal. And what is given is that uh, the apple tree is quite young, so only 2 apples will grow on it, and apples will grow in certain vertices. And after the apples grow, Timothy starts shaking the apple tree until the apples fall. And let the apple now be at vertex U. If the vertex U has a child, the apple moves to it, and it can move to any of the childs if there are many of them. Otherwise, if there are no child, apple falls from the tree. So basically, you will be given 2 apples, the positions of the 2 apples, which vertices the 2 apples are residing on, and you have to count in how many ways, like how many leaf vertices through which these 2 apples can uh, come out or exit out. What is the total number of ways, like the total number of pairs of vertices AB through which they can come out. Like the A is the first vertex from which the apple will come out, and vertex B is the second, the leaf or the vertex through which the second apple will come out. Okay, so let us see how we can do this. So basically, you are given a tree, right? You are given a tree which is rooted at node 1. So let's say your tree looks like this. Okay, and you are also given the positions of 2 apples. So let's say the first apple is at this node, and let's say the second apple is at this node. Let's label these nodes as X and Y. So what you do, you just keep on shaking these tree. So in each shake, the apple will fall to one of his children. So let's say once you shake this for one time, this this apple will either go to this or this. Similarly, this apple will go either to this node or to this node. It can go to any of them. So we have to find in how many ways these 2 apples can come out of of this tree, right? So one thing, if you observe that this apple can come out only of these 2 nodes, right? And similarly, this apple will come out either from this node, or this node. In general, what you can say is that a apple at vertex V will come out from any of the leaf nodes in its subtree. Okay, an apple at a vertex V will come out from any of the vertices, or like from any of its leaf vertices in its subtree. So if you consider this node X, how many ways, or like how many leaf nodes does this node contain? Let us call that as leaf of X. So, and similarly, let's say how many leaf nodes does this node contain? Let us call it as leaf of Y. So if there are leaf of x ways for this apple to come out, and if there are leaf of y ways for this apple to come out, so the total number of ways in which both the apples will come out will be nothing but the combination of these two, that is leaf of x into leaf of y. Okay, so you will see, you can see that you might say, okay, this was the case when x and y are at the distant, or are at different subtrees. Okay, you might say that this is the case only if they are at different subtrees. What if x x is containing y? What happens in that case? Let's say y is contained in the subtree of x. So what happens in that case? So even that case, you can see one thing, that for node y, there are like leaf of y ways for this apple to come out, and similarly for node x, there are like leaf of x ways for this apple to come out. So basically the leaf from which this apple or this apple come out are independent. So that's why we can multiply them in order to find the total number of ways in which both the apples will come out. So all you need to do is to basically pre-compute for each node how many leaf nodes does it contain, right? For each node, how many leaf nodes does this contain? And for finding this, you can use DFS. DFS, start your DFS from the very first vertex, and if let's say you are at some vertex V, and you want to find what are the total number of leaf nodes does this vertex contain, you call DFS from each of these nodes, and after finding the leaf nodes for each of its child vertices, you just simply add the leaf nodes to its parent, right? So kind of leaf of vertex V will be nothing but how many leaf nodes does each of its children V contain. Okay, where V is a child of V. Sorry, let's call it V dash. Okay, so the count of leaf nodes a vertex V contains is nothing but the count of leaf nodes each of its children contains, the summation of it. Okay, so let us see how you can implement it in code. So basically you take n, and then you take all the edges. So there is a edge between u and v, then adjacency of u dot pushback v and v dot adjacency of v dot pushback u. After that there are q queries. So this was important. So basically you are not just given a single x and y, rather you are given two, like x and y in the form of queries. There are q queries, and for each query you need to answer. So that's why we are pre-computing the leaf nodes, like how many nodes, how many leaf nodes does a vertex contain. So here we have made a DFS function. So this DSS function contains the source node, the parent of it, adjacency list, and the leaf nodes, and the leaf list. So for every adjacent vertex in of S, I check if it is a parent, I just continue. Otherwise, I run a DFS from E, passing parent as S, and then I add leaf of E to leaf of S. Okay. Now I have also maintained a variable any. So when will you call a vertex as leaf node? You will call it as a leaf node only if it has no child vertices. So initially I initialize it with false. So if there are any child vertex of it, so any will become true. So at the end I check if no vertices are leaf, no child vertices are there of this vertex S, then it's a leaf node, and hence I increment its count. And at the end, once you pre-compute it, you just take x and y, and the total number of ways will be leaf of x into leaf of y. Okay, so does anybody have any query on this or doubt?
Can both the apples exist in the same node?
I think yes. Let me check. I think yes. Or like even if they are not on the same node, they will never be on the same node at all as well. So there is just given x and y. There is no constraint that xi has not to be equal to yi. And also here also there is no such restriction that a vertex cannot contain two apples at the same time. Okay, it
Okay.
can't. Yeah. So yeah, they can contain the same a vertex can contain two apples simultaneously. Okay, or also you can see one thing that if the positions of the apples are different, so it won't ever occur that a single node is containing both of the apples. For example, if let's say your apple is at this node and the another apple is at this node, so even if after one time this apple will come to here, then this apple will come to somewhere down. So it can't happen that both the apples are at the same node at the same time until and unless the
Sir,
initial yeah.
it is written in the question, it will be on the same note.
What?
It is written in the question that both apples could be on the same note.
Where?
So, in the third paragraph, in the bracket.
uh yeah. So it's written that apples will grow in certain vertices and these vertices may be the same. Okay, so that's why it does not matter like here. Okay, so they may be on this.
And what if any apple is present in the leaf node? Then also it consists only one leaf. We'll consider.
Yeah, like if there is a apple on a leaf vertex, then definitely there is just one way. Since it's a single node, so leaf of that node will simply be one. So just there is just a one way for that node to come out. So once you shake the tree, it will simply come out, right?
Okay.
Yeah. Okay, so that's why you just try to find out how many leaf does X contain, how many leaf does the subtree of Y contain, and multiply them together. Because the leaf from which comes out and the leaf from which Y comes out are independent. Okay. So if there are no further doubts, we can move to the problem E, right? Which was tracking segments. So in this problem, you are given an array A consisting of n zeros, and you're also given a set of m, not necessarily different segments, and each segment is defined by two numbers li and ri, right? And that represents a subarray ali to a of ri of the array A. Now we are calling that a segment li to ri is beautiful only if the segment contains strictly greater number of ones than zeros. For example, if you consider this array, then the segment 1 to 5 is beautiful because see there are three ones in total and there are two zeros. So 3 is greater than 2, hence it's beautiful. But the segment 3 to 4 is not beautiful. Why? Because this 3 to 4 contains 1 0 and 1 1, right? So they are not uh, one is not strictly greater than zero, the count of zero, so it's not beautiful. Now you are given q changes. In each change you will be given an x, and what you will do is simply replace a of x with 1, right? And what you have to do is to find the first change after which at least one of the m segments becomes beautiful. Okay, so what it means is that you have to find out the first instant when there exists at least one segment which contains strictly greater number of ones than the number of zeros. Okay, so let us see how we can do this. Okay, so let us say your initial array contains only zeros. Okay, like this, and then you are applying the changes one by one. So let's say you change this to 1, then you changed this to 1. Okay, and there are also certain segments given like this. Okay, so you have to check whether there exists, like you apply a change and then you check whether there exists at least one such segment which contains strictly greater number of ones than the zeros. For example, once you apply these two operations, that is you replace this and this positions with 1, you can clearly see that if you consider this segment, it contains two ones and 1 0. Hence this segment is a beautiful segment. So what it means is that once you reach this query, or like once you reach this state of change, then afterwards the array will always be beautiful. So you have to print minimum such position, or like minimum such instant of time, or like minimum such instant of time where greater ones than zeros. So one way you can do this is just do a linear thing. That is, you take x, replace a of x with 1, and then again check whether for any segment it contains strictly greater ones than zeros or not, right? But but before that, let us see how we can ensure that how we can check whether there is exist at least one such segment which contains strictly more ones than zeros, right? So let's say what happens if our array was static. Let's say our array is this and this is fixed, and we just have to check whether there exists at least one such segment which contains strictly greater ones than zeros, let's say. So what you can do is that you can pre-compute the prefix sum on it, right? Once you compute the prefix sum on it, you will get something like this: 0, 2, sorry, 0, 1, then 2, then 2, and then 3. So this will be the prefix sum on it, right? Now, in order to check how many ones does this index, this segment contain, you simply have to do, let's say this was index R and this was index L. So in order to find how many ones does this segment contain, you simply find P of R minus P of L minus 1. So this will be the number of ones. Similarly, you can find the number of zeros in this segment. So how many zeros it will contain, you will find what is the total length of this segment minus the number of ones, right? Once you compute these two things for this segment, you check if the number of ones is greater than number of zeros. If it is so, it means that this segment is beautiful. Okay, so I can see some queries. Okay, no queries. So in this way, if you are given some array which is static, which means that the values of AIs are fixed, and you just have to check whether there exists any segment which contains strictly more ones than zeros. What you can do is you can simply compute the prefix sum on it. After computing the prefix sum on it, for every segment L to R, you find what is the number of ones, what is the number of zeros, check if number of ones is greater than 0. If it holds for any segment, it means your entire array is beautiful. Okay, so in
But
this way,
when
yeah,
but when we are
yeah,
applying the prefix sum, it will take big of n time,
yeah,
and for the queries we are taking big of n time, so it
yeah,
will be n square.
yes, correct. So there will be order of n queries, and for each query you are computing the O of n prefix, and then again you are checking for every segment like whether it is a good or not. So overall it will be like O of n square or O of n into m kind of thing, but still a lot has to be done to optimize it. So the optimization here is that instead of computing the changes linearly, right? What you are doing is that you are applying the 0th change, then 1th change, 2th change like this, and at a moment when you start seeing that okay, now my array is beautiful, you stop at that very point, and whatever is the index, you return that index, right? So the state of your array will be something like this. First of all, your array will not be beautiful, not be beautiful, not be beautiful. Then after that, it will be start becoming always beautiful ahead. Okay, so what you can see here is that the array is not beautiful at still some point, and after that it starts becoming beautiful. So all you have to do is to find the index of this first true value, that is what is the first instant at which your array starts becoming beautiful. So you can use actually here binary search. Okay, why? Because let's say you set your low and high at this point, and by finding the occurrence of mid, you can actually reach this position. How? Let us say your mid is at this value. So if your mid is at this value, you know that your array will be beautiful, and you can easily check whether it's a beautiful or not in O of n using prefix sum at this mid, right? After that, if it's a beautiful, you will go left of it, right? On the other hand, if your mid was at here, you can go to right of it. Okay, so that's why the intuition here is to use binary search. Okay,
So first of all, we have to apply all the queries. That means
no,
it's
no,
for
no,
all the ones we have to
don't
put.
apply queries at the same time. Rather, let us say your low is 0, and let's say your high is equal to q minus 1. So these are the zero based indexing of the queries, right? Now you find the mid. Okay, you try to check whether if I apply all the operations till mid, is my array started becoming beautiful? So when you are fixing your mid, you apply all the queries from 0 to mid, right? So after applying all the queries, your array will start looking like this, right? Now, now this array is fixed, and you know very well you can compute in around order of n plus m. The You can compute in order of n plus m whether there exists any segment which is containing strictly greater ones than zeros. So if it comes out to be true, or like if there exists at least one such segment which is containing greater ones than zeros, then it means that yes, at mid you can do. So for now, you can set your query position to mid, and you can move to the left of it. That is setting high to mid minus one. Otherwise, if there is no such segment which is containing strictly
Sorry,
more ones
sorry.
than zeros, yeah,
Please repeat. Means first you are checking that whether the whole array is beautiful or not.
yeah. No, no, no. Here
Yeah.
actually what I'm saying you is that try binary searching on the query index. So obviously the initial array is containing only zeros. So definitely it can't be ever beautiful by itself, because there is no question of having strictly more ones than zeros, because there are no ones at all, right?
Yeah.
So we are basically binary searching, because so let's say at the zeroth query, like after applying the zeroth change, your array is not beautiful. Then you apply the second change. Let's say again it's still not a beautiful array, so that is false. Then let's say after applying the second query, your array starts becoming a beautiful. So if it is beautiful at this
How
point
do
of
we
time,
know? How do we know?
so for knowing this only, we are using this binary search. So let's say we are our mid is at this point, that is 2. So
Yeah.
what we do is that we apply all the changes from 0 to 2, right?
But won't that be lock you into queue complexity?
No, like we are since binary searching,
हाँ,
so
तो
it
that
will
will be
be
lock queue.
log of q, yeah,
And then
multiple.
for every query, we are gonna iterate towards all the previous queries, like keep उससे
हाँ.
पहले कौन से index है, that is queue, right?
Yeah, that will be q.
Yeah, so to generate the current array,
Yes, yes, yes.
and then we'll have to traverse the whole array. मतलब that's
Yeah,
gonna be O of n, q into n,
yes.
q of
No,
q
no,
plus.
not q into m. So see, once you apply all the q operations, like once you set your mid, you apply all these operations, right? So in worst case, mid can be q. After you apply all these operations, then you run another loop to check or to find its prefix sum. And
हाँ,
after
okay.
finding the prefix sum, you again iterate on all the segments.
Okay, so that is
So
gonna
kind of,
be,
yeah,
yeah, q plus n plus m. Okay, yeah.
yeah. Okay, so
So on every mid we are again rechecking the whole like prefixum.
hmm, basically once you fix this mid, you apply all the changes till mid. After applying the changes, it will be some static array like this 0 1 1 1. After that, you compute it prefix sum. After computing the prefix sum, for every segment, check if it contains strictly greater ones than zeros using that prefix sum only. If it holds for any of the segment, it means that you are standing at a true, means it has become beautiful now, so you don't need to go ahead any further.
So we are reducing it from n square to n log n log n. Yeah.
Yeah, basically the search space का size q है, so you will be encountering log of q, and then in each iteration, like after fixing each mid, you apply the q operations, then you compute the prefix in O of n, then you iterate on all the segments in O of m. So overall it's log of q into q plus n plus m. Okay. So does anybody have any doubt like in this or the time complexity of it, which I told you?
No.
Okay. So I guess that the intuition behind the binary search is clear to you, right? That why we are binary searching on true on the queue, the index of the first position. Okay. So let us now move to its code. Yeah. So as you can see here that what we are doing here is that first of all taking n and m, then I am taking all the m segments. So these are all the m segments, li and ri. After that I am taking all the q queries or q changes. So I am storing in val, and I am making everything zero based indexing. That's why you see here I have decremented L and R here by 1, and also I have decremented the positions of the changes by 1 as well. Now I am setting low as 0, high as q minus 1. Initially my answer is minus 1 if it is not found. Then I am computing mid while low is lesser than equal to high. Then I apply all the changes from 0 to mid, and that is done by simply creating another array B, which is all initialized to 0, and then setting B of val of I is equal to 1, right? After that I use my B array itself as a prefix sum array. So that's why I add the value of B of I minus 1 to BI, and after that I declare a flag false, or this boolean variable f. So for each of the segment from 0 to m, for each of the m segments, how many ones it will contain. So that will be nothing but prefix sum up to ri minus prefix sum up to li minus 1. So li minus 1 only if li is strictly greater than 0, otherwise it is 0. Then zeros will be what is the length of this segment, that is r minus l plus 1 minus the count of ones. So if ones is strictly greater than zeros, it means yes, we got some segment. So f is true and break. So if f is true means this is beautiful array. So for now I set my answer to be mid, and I make my high to be equal to mid minus 1, otherwise low is mid plus 1. At the end I check if answer is not minus 1, then I increment my answer because I have to print in 1 based indexing. So I print the answer finally. Okay, somebody is saying that intuition behind prefix sum. Okay, see, if you don't use prefix sum and if you naively calculate the sum of all the numbers from L to R, it will take you order of R minus L plus 1. Okay, so if I give you L as 0 and L as 1 and R as n, it will take you O of n to compute the prefix sum. It will take you O of n to compute the sum of all the numbers in this range. But if you just compute the prefix sum, you can compute all the sum queries from L to R in O of 1. Okay, that is if you want to find out. So let's say if you want to find out the sum of all the numbers, or like all the AI values from L to R index, you can simply say prefix of R minus prefix of L minus 1. So this will give you the sum of all numbers from AL to AR, and you are computing this in O of 1. So just as to optimize our time complexity, we are using prefix so that for any segment we can compute its sum in O of 1. Okay, so somebody is saying me to show the binary search part. Okay, sure. So see, this is the binary search part. Okay, so in binary search what we do is that we run a loop while my low is lesser than or equal to high. So low is set to 0, high is set to q minus 1. I compute the mid value, right? After computing the mid value, you apply all the changes till mid. So that's why run a loop for I is equal to 0 till mid. and update the b values, that is set them to 1. Then I am computing this prefix sum. After that, I am iterating on all the segments, computing how many ones it contains, how many zeros it contains, checking if ones is greater than zeros, and setting f as true accordingly. So if any segment is there containing strictly more ones than zeros, then answer will be mid for now, and you move high to mid minus 1. Otherwise, you definitely need to move ahead. So low is equal to mid plus 1. Okay. Okay, so I hope you got it right. So let us move to the next problem if there are no further queries. Okay, so this problem F1 is OMSK Metro. So this is the easier version, and in this problem U is given as 1. So let us first see what this problem says. So although this problem says a lot of things, okay, I will summarize this for you and tell you what this actually problem contains. You can read this problem as well. Okay. So in this problem, what it's given is that two are initially standing on a vertex 1. Okay. And what we are doing is that we are creating a tree on it. Okay. So we will be sequentially adding vertices to this tree, like 3, then 4, then 5, like this. Okay. So we will be sequentially adding vertices or nodes to this tree by adding edges, and each node will be having some value. So the value will be either +1 or -1, each of these nodes. And it's given that the initial value that this first node will be containing will be nothing but 1. Okay. Now we need to apply like Q changes, or like you can also say Q queries. In each query, you will be given either a new vertex to add. Let's say you will be given some vertex. Let's say you have formed your tree till this point, you will be given some vertex. So let's say you are given some vertex 4. Now what you have to do is that you have to add a new vertex to this. So till now you have added 5 vertices. Next you will be adding vertex number 6 to the vertex 4, right? And you will also be given what will be the weight, or like what will be the value of this vertex. So let's say the vertex is +1. Similarly, each of these nodes will be containing some value like this. Okay. So this is the first type of query that you can do, right? That is, what you will do, you will choose some vertex, and after that you will append a new vertex to it and add some cost to it. So these queries are given in this form, that is plus v and x. So plus v and x denotes that whatever is the tree formed till now, choose vertex v from it, and then append another vertex with a weight of x, and the number on this node will be like whatever is the total number of nodes on the tree plus 1. So this is the first kind of query that you can do. The another type of query that you need to do is that, let's say you have formed your tree like this. Okay. After that you will be given two vertices u and v, and some number k. So what you need to do is that you need to consider a simple path between u and v. So let's say this is the simple path between u and v. Now what you have to do is that you have to check whether there exists any segment of this path. So let's say this is one such segment of path on the segment of this path. So you consider this segment of path of nodes, try to calculate the sum of the values written on these nodes, and check if it can be made equal to 1. So let's say these are like the values does which this node contains. Okay. So if you consider this vertex, which is u, this vertex v, and let's say your k is given as 2. Let's say k is given as 2. Then what you can see is that if you choose these vertices, this subsegment of this path, okay, the one which I am underlining in blue. So you can clearly see the sum of all the nodes on this path is +1, -1, +1, +1. So this comes out to be 2. Okay. So basically you have to check whether in the path between u and v, is there any subsegment or basically continuous path on the nodes on the path whose sum of all the values is k. So is this two types of queries clear to you? Okay, somebody saying u or v are not included. No, u and v may be included or may not be included. The important thing is that you have to consider the path between u to v. So let's say this is let's say a path between u and v. Okay, so what is a subsegment? Subsegment means any sequence of nodes on this path, continuous segment of nodes. So this is one such subsegment, or maybe this is one such subsegment. This is another such subsegment. So basically you consider the path between u and v and consider all the subsegment of nodes on this path and compute the sum of values on written on these nodes, and you have to check whether the sum of all the nodes on that subsegment can ever be equal to k or not. Okay, so in this problem it's easier version, so u is always given as 1. So what it means is that your u is always 1 and v will be something else, and you just have to consider the path between u and v, sorry, the path between 1 and v, and check if there exists any subarray or like this subsegment of nodes whose sum is equal to k or not. Is this clear? Okay, this is clear. So let's see how we can do this, right? So let's say if we maintain the prefix sum, let's say if we maintain the prefix sum, okay, if we maintain the prefix sum. So let's say prefix sum is what? Prefix sum is like if you consider some node u, so prefix sum of u will contain the sum of all the nodes in the path from 1 to u, right? So if you know the prefix sum of all the vertices which lie in the path between 1 and v, what you can do is that you can simply check whether for any two vertices on this path, if you took any two vertices on this path, and if it comes out that prefix sum up to, let's say this vertex is v1 and this vertex is v2. So if it ever comes out that prefix sum of v1 minus prefix sum of v2 is equal to k, then you can definitely say that the sum of all the vertices on the path on this path will be equal to exactly k. Okay, I can see some query. Okay, you know, so this is the prefix sum. First idea is prefix sum. So what we can do, we can maybe we can maintain a prefix sum. Also, what we will do, we will initially add a dummy root or like a dummy node with a value of 0. Why we are adding a dummy node, I'm telling you. Let's say once you add a dummy node, the reason we are adding is that it might be possible that you consider this subsegment. Okay, if you consider this subsegment, then you can say that prefix sum up to this node, let's say u minus the prefix sum of the dummy node. Okay, so that will give you the sum on this path. So you can also check whether this is equal to k or not. Okay, so this was one thing, but this will actually take O of n. Okay, this will actually take O of n to see whether there exists any such pair on the path between 1 to v, because once you are given some v and you have to check whether there exists any such pair or not. First of all, you have to compute this prefix sum for each of its parent. So you have to you have to keep on moving to each of its parent and find out what is the prefix value of that node. So you compute this entire path prefix sum for each of the node on this path. You have to first of all store, and after that you have to check this thing. So even by using some optimization or using some maps, it will again take you O of n in the worst case. So overall, it may go as O of n square. So definitely we have to optimize this. Okay, we cannot simply like store all of these prefix sums on the path from 1 to v and do something. So what is the optimization? So the optimization is like this, that if you see, the values are only +1 and -1. Okay, so how does it help? So let us say you are initially at the dummy node, which was node number 0. Okay, then you have node 1, then let's say 2, 3 and 4, like this. Okay, so you know that initially at the node 0 there is a cost of 0. Now at node 1 there is like value of 1. Now let's say it is -1 on this, +1, and let's say +1 again. Okay, so start with this node. So initially you are at 0. Okay, let's draw it on a number line or like some coordinate system. It's 0. Then from 0 you move to 1. So your prefix sum become equal to 1, right? After that you move to this. So the prefix sum becomes 0 again, right? After that you move to this. So your prefix sum becomes equal to 1. And after that you move to this. So your prefix sums become equal to 2. So 0, 1, 0, 1 and 2. So what you see is that your prefix sum is varying continuously. So if currently your prefix sum is x, in the next iteration it will be either x plus 1 or it will be x minus 1. It can't go like x plus 2 or x minus 3 like this. So what it means is that, let's say if at this node your prefix sum was, let's say, 3, right? And if at this moment of time, let's say your prefix sum is 5, then we can definitely say at some point of time between these nodes, I would have reached a prefix sum of 4, right? Similarly, if let's say this was 15, then definitely I can say between these two nodes, between this node and this node, I would definitely have reached 4 in between them, or any number from 5 to 15. Any number between 5 to 15, I will have reached the prefix sum of this in between these two nodes. Okay, so if that is the case, then what we can do is that we can just maintain that. So basically, let's say if you consider this path, let's say if you are having a prefix sum of, let's say, 3, okay, and if you are having a prefix sum of 16 somewhere else, right, then you can have any prefix sum from 3 to 16 in between this. Okay, but what you want that, and let's also maintain the case that this is greater than 16. Okay, so what you want that prefix r minus prefix l should be equal to k. Okay, so let's say k was equal to 15. Let's say k was equal to 15. So here what you say, if there was one node at which I was having prefix sum 3, and then some later point of time, if I have a prefix sum of, let's say, 16, then I can definitely say that uh, 3 to 16, what is the difference? There is a difference of 13. So if k was equal to 13 or even lesser than 13, then definitely I can always choose 3 and 3 plus k. Okay, what I'm saying is that if you you know that there is 3 and there is 16, the difference of which is 13. So if any k is given which is lesser than or equal to 13, then definitely I can make this PR minus PL to be equal to that k. The reason is that I can choose 3 and then I can choose 3 plus k. So 3 plus k will definitely lie in between these two. Okay, because as I said that if you are having 3 at some point of time and 16 at some point of time, so the prefix sum will definitely at some point of time will at one point of time will reach 13.
In just a sec, like, can't we do this that for every node we store the like if we are solving f1, as we know that u is 1 always, right? So
Yeah.
for every node we store what is the minimum and the maximum sum that we have achieved till that node. Okay.
Yeah.
So if we are given a query 1 comma let's say 5, so just we can go to 5, we check if k lies between this minimum and maximum, and if it does, then it's a yes, else it's a no. Would this work?
K lies within that range.
For every node, if we have a minimum maximum, I guess that would be simpler to implement, no? And अगर उस path पे minimum maximum lie कर रहा है, so if k lies between those numbers, then k must have been achieved somewhere, right?
I did the same, but I got the wrong answer.
Okay, you are saying if k is lying between the minimum and the maximum one. Okay.
Subsequence के लिए
No,
मतलब
actually it's not true always, I guess, because minimum and maximum, the order is also important, because let's say 0, then let's say -1, then -2, then -3, and then let's say what -2 will be again -1, 0, 2. Okay. Mm. If k lies between minimum and maximum prefix sum, you are saying.
अच्छा, no, I don't think it would. It's I guess if you could consider the case that if we go from 0 to -4 and then we go 3 up, okay, so the minimum would be -4 and the maximum would be 0, right? And if k is 3, for example,
Okay.
so in our case we have gone from -4, we first went from 0 to -4, then -4 to -1. But -4 to -1 is an increment of 3. So if k was 3, we would have achieved 3. But minimum maximum won't work, yeah.
Yeah, that's why only minimum maximum won't work. Like what you have to do here is basically maintain two things. The first one is like maintain this increasing thing. Okay. That is, what is this maximum difference? What is this maximum difference on the path? That is, let's say first you got 3 and then you got 60. What is this maximum difference? So we are considering first the case where k is positive. So let's say k is 3, 4 like this. So in that case, what you want is that your PR minus PL should be equal to 3. So this is a positive quantity, right? So this is greater than 0. So it means PR should be greater than PL. Okay. So the node which you encounter previous and the node which you encounter later, so the latter node should be greater than the previous node. So let's say k is positive. So it means that if you consider the nodes in the path from 1 to u, so let's say these are my L and R. So
But
what you
again,
want?
coming to this, like minimum max, like we need to get the maximum difference, right?
Yeah, we need to get the maximum positive
Maximum difference
difference.
would always be between the minimum element on the path and the maximum element, maximum sum and minimum sum.
Not always true, because let's say this is having a value of minimum and this is having a value of maximum. So you can't say that it's actually max minus minimum, because maximum is occurring previous and minimum is occurring ahead. Right. So you can't say
Okay, we
that
are
this
coming from down up, or we are coming from the top, right?
Yeah, we are coming from the top and we are considering first the case where k is greater than 0.
Okay.
So if k is greater than 0, then PL has to be strictly lesser than PR, or you can say PR has to be greater than PL.
Okay.
So first of all, considering this case, you try to find what is the maximum difference. Okay. And if that maximum difference is at least k, you are done. Otherwise, if k is strictly lesser than 0, then you try to find the maximum difference between the minimum difference between PR and PL, and definitely in that case PR will be lesser than PL. Okay, so let's say k is equal to -3. So you try to find out the minimum value of this PR minus PL. So let's say it's -4. So if this k is lesser than or equal to this minimum difference, so in that case you would be able to do or achieve the thing.
Like, can you take can you do a dry run for a query? Like, how we
Okay.
gonna achieve this? Yeah.
Okay, so let's query on this. Okay, let's try run on this. So initially you are having one node. Okay, let me.
I guess let's
Okay.
just build the tree and then just query, no?
Yeah. So you are initially having node 1, then
One is
there is
connected
node
to 2,
2,
3, 3 is connected to 4, 5, 6.
is connected to 3. Then sorry.
2 is not connected to anything.
Yeah. Then 4,
5.
5, and then 6. And all of these are like 1, -1, 1. And these are like -1 and -1, and this is 1. Okay. And let's say, sorry. Okay. And let's say this was, there was also node 0 with 0. So if you compute the prefix sum, so this will be 0, 1, this will be 0 only, then this will be 0, 1, then this becomes
So can you
0,
maximize the screen?
-1, 1.
Maximize the screen.
Okay. So let's say your initial graph looks like this. Okay, I have computed the prefix sums. Then the query is, let's say, at 6, right? So as you can see here, what is the maximum value of PR minus PL on this path? So you see, if you take this two nodes as L and R, so you will see PR is 1 minus PL is 0. That is 1.
Yeah.
So that's why it's possible in this case.
Okay.
Okay.
Now if you
So
come to 3.
okay, for example, if you come on to compute for 3, and what is the value of K?
Let's just like let K be something. No, what is
Okay,
the
let's say
maximum
K
difference
is
that we can get?
2. So K is 2. Then what is the maximum difference between any two nodes in this path? So you see it's again 1.
Yeah.
So, but 1 is not greater than or equal to 2. So it means it's not possible in this case.
Okay.
Okay.
And this would work for negative cases as well, if K is negative.
Yeah. If K is negative, then in that case you find the minimum value of PR minus PL.
Okay. So if
So for example, in this case, you see what is the minimum value? So 0 minus 1, because if this is your let's say L, sorry, this is your L and this is your R, then PR minus PL will be -1.
no, if L is yeah.
-1.
No, L is 1, no, at
Yeah, L is PL is 1. Okay,
PL is
PL
1,
is 1.
PR is -1.
PR is 0.
PR is 0. Yeah, sorry.
So PR minus PL minimum value will be -1.
Okay.
So that's why in this case it's possible.
Okay. And if you just connect a 7 to a 6, okay, just connect a 7 to a 6.
Okay, what are you saying is that connect 7 to 6. So
And
let's
just
say
give
we
it
connect 7. Yeah. What is
and
the
just give
weight?
it 1.
1. So the prefix sum will be 2.
Yeah.
Right?
And if we want K key value should be 2,
Yeah. K,
so the
K is
maximum
2.
difference that we can get is 2, 0, right?
Yeah,
2
2
minus 0.
comma 0.
So it is possible.
Yes.
Okay.
If you give K is equal to 1, still it is possible, because here you are having 0, here you are having 2. So definitely in somewhere between the path you will achieve 1.
Okay. Got it.
Okay. So that's why
Hmm.
I'm saying that if at some point you are having, let's say, PL, and at some point you are having PR, such that let's say the difference between PR and PL is some, let's say, 10. And so for any value for K which is lesser than or equal to 10, you can also achieve PR minus PL is equal to that K.
But इसके implementation में can't we do this that like if you just go up and then कि हम prefix sum का minimum maintain कर लें?
डेफिनेटली वो तो करना पड़ेगा, प्रीफिक्स सम का मिनिमम और प्रीफिक्स सम का मैक्सिमम भी करना पड़ेगा, प्लस
negative cases you would require the prefix of maximum, right?
yeah, prefix sum maximum, maintain prefix sum minimum, and also you need to maintain one thing, that is, let's say you are considering some vertex v, so you have to consider, like, for any two pairs of like segments, what is the maximum difference in pl minus pr, sorry, pr minus pl, and what is the minimum difference of pr minus pl, like among any two nodes on this path. So let's call this as difference max, and let's call this as difference min. Okay, so let's try to compute these things one by one. So the first one was the maximum sum of v. So obviously maximum sum of v will be simply maximum of, like, whatever is the prefix sum up to v, prefix sum up to v, comma, like, what is the maximum sum to the parent of v, right? So let's say this was v, this was, let's say, the parent of v. So I want to compute, like, what is the maximum prefix sum among all these values. So either it will be the prefix sum of v, or like what if is the maximum till this point, right? Similarly, you can also calculate minimum sum of v in the same manner, simply taking minimum. Now how you will calculate difference max of v? So difference max of v means what? Consider the path from 1 to v. You have to calculate the maximum difference of pl minus pr. So that will be nothing but either you take difference max, sorry, either you take difference max of the parent, right? The difference max of the parent, or you can choose this as one of the endpoints. So in that case, it will be like prefix sum of v minus, since you want to maximize this difference, you have to take the minimum prefix sum till parent of v, right?
Got it.
In similar way, you can also calculate difference minimum till v.
Like, just can you explain like maximum, minsum wala, how
Yeah.
did you get?
See, maximum sum and minimum sum are simple. Like consider 1 to, let's say, v. Okay, so max sum of v is nothing but, like, all the nodes which are contained in the path between 1 and v, you have to take the maximum prefix sum of that.
Okay.
Similarly is the
Okay,
min
it
sum.
does like उस prefix sum में जो भी maximum आ रहा है.
Yeah, maximum prefix sum in a path between 1 to v.
Okay. Yeah. Okay.
And right, so these were max sum and min sum, and then there is difference max and difference min. So difference max is like, consider all the pair of nodes, what is the maximum difference that you can get.
अच्छा, and we are just checking कि अगर हमारा जो current v वाला node है, that is the like in the prefix sum v वाला thing, we are considering that we are maintaining it as L, right?
R, not L, R.
R minus L, and we are getting the L from the right. Okay, yeah.
So like either the maximum difference will be attained till the parent of v, so that's why difference max parent, or if this is the parent, then you have to take them in. That's why it's necessary to maintain this.
Yeah, how did you get the intuition to solve this essay?
So I was not getting intuition for a long time, but I have solved similar problem where see, if the problem was like values can be anything, like AI can be anything, then I don't think I would have been able to solve it. But the thing that is +1 and -1 gives you an intuition that it will be continuous. The prefix sum will be continuous, right? So if you have read in JE or like differentials that if at some point of time fx is, let's say, negative, and if it's some other point of time it is positive, then in between these two x1 and x2 it must be 0 somewhere. Okay, so that give me the intuition that if prefix sum is, let's say, at some point 3, and if some other point it is 10, so even though it will go down, at some point of time it will have to reach this 10. So it means that any prefix sum from 3 to 10 is achievable. Okay, so that's why that give the intuition that okay, you only need to consider what is the maximum difference you can get, because otherwise you can always get any prefix between 3 to 10. So that's why we are maintaining this maximum difference and minimum difference.
Got it.
Okay.
Thanks.
Yeah. So I can show you the code for the same. Okay, so here I've declared this maximum and minimum. So that will be used for storing the maximum and minimum prefix sum. So for node 1, it is very clear that the minimum prefix sum would be 0. That will be the for the dummy node, and maximum prefix sum would be 1. That is for the node 1 itself. Then I am also maintaining what is the sum of all the values of the nodes on the path from 1 to v. So sum of 1 will be 1. Then these are like difference max and difference minimum. Difference minimum of 1 would be 0, and difference max of 1 would be 1 itself. Take the queries. If it is a plus query, v and x, then I am having a pointer. What is the label of the node that will be added? So minimum of this node will be initially I am initializing is to sum of v plus x. So sum of v plus x is simply the prefix sum up to this pointer node. So initially minimum of pointer and maximum pointer are same. Then I'm taking minimum of pointer with minimum of its parent, that is v. Similarly, maximum of pointer is max of pointer and max of v. Then I am calculating difference max of pointer. Initially difference max of pointer will be difference max of its parent, that is v, and similarly difference min of pointer will be difference min of its parent. Otherwise I can take this node, so it will be maximum of difference max of pointer, and this is the prefix sum till this node minus the minimum of its parent. Similarly, difference minimum will be minimum of this difference min of pointer, and what is the prefix sum till this node minus maximum till its parent. And at the end, I also update the sum till this prefix sum till this pointer. At the end, when I get a query of second type, if k is 0, it's always possible empty subarray is allowed, empty path is allowed. Otherwise, if it's positive, I check if the difference max is at least k, print yes, otherwise no. Similarly, if difference min is, if k is negative, then you have to check if difference min is lesser than or equal to k, then only the answer is yes, otherwise it's no. Okay, so does anybody have any doubt in this? Okay.